ensuring that applications run smoothly across multiple environments. Where is Kubernetes used? Kubernetes is used in various environments, including public clouds, AWS, Google Cloud Platform, GCP, Microsoft Azure, private data centers, on-premises infrastructure, hybrid clouds, combining public and private cloud environments, edge computing, managing containers on edge devices. When was Kubernetes created? Kubernetes was initially developed by Google and released as an open source project in June 2014. It became a part of the Cloud Native Computing Foundation, CNCF, in 2015. How does Kubernetes work? Kubernetes works by orchestrating containers through a set of abstractions and tools. Pods, the smallest deployable units, which can host one or more containers. Nodes, machines, virtual or physical, that run pods. Clusters, groups of nodes managed by Kubernetes. Controllers, maintain desired state by managing pods and nodes. Services, expose applications running on pods to the network. Kubelet, an agent that runs on each node and ensures containers are running as expected. Kucommand line tool to interact with the Kubernetes API server. Who created Kubernetes? Kubernetes was created by engineers at Google, notably Joe Beda, Brendan Burns, and Craig McLuckie. The project drew on Google's extensive experience managing containers with their internal system called Borg. Why was Kubernetes created? Kubernetes was created to solve the complexity of managing containerized applications at scale. As container adoption grew, there was a need for a platform that could automate and streamline deployment, scaling, and operations, leading to the creation of Kubernetes. History of Kubernetes. Google developed and used an internal system called Borg to manage its containerized applications. 2014, Kubernetes was announced and released as an open source project. Kubernetes joined the CNCF, gaining wider community support and development. 2016 present, Kubernetes has become the de facto standard for container orchestration with widespread adoption across industries. Kubernetes ecosystem. The Kubernetes ecosystem includes a variety of tools and projects that enhance its functionality. Helm, package manager for Kubernetes applications. Prometheus, monitoring and alerting toolkit. Istio, service mesh for managing microservices. Operators, custom controllers to manage complex applications. KubeVirt, manage virtual machines alongside containers. Minikube, tool to run Kubernetes locally for development and testing. This ecosystem fosters innovation and extends Kubernetes capabilities, making it a robust and versatile platform for modern application management. In depth on Kubernetes. Kubernetes architecture. Kubernetes has a robust and modular architecture consisting of several key components. 1. Master node, control plane. API server serves the Kubernetes API and handles communication with the cluster. etcd, a distributed key value store used for configuration data and state management. Controller manager runs controllers to manage the state of the cluster, such as replication controllers and node controllers. Scheduler assigns pods to nodes based on resource availability and policies. 2. Worker nodes, an agent running on each node that communicates with the API server to manage containers. Kubeproxy manages network routing and load balancing for services on each node. Container runtime, software responsible for running containers, such as Docker or Containerd. Hash Kubernetes concepts. Namespaces provide isolation for resources within a single cluster, allowing multiple teams to share the same cluster without interference. Config maps and secrets, mechanisms to manage configuration data and sensitive information separately from application code. Ingress manages external access to services, typically HTTP, and can include load balancing, SSL termination, and name-based virtual hosting. Persistent volumes, abstraction for storage resources, allowing stateful applications to persist data beyond the lifecycle of individual pods. Custom resource definitions, CRTs, extend Kubernetes functionality by defining custom resource types. Kubernetes deployment models. 1. Standalone clusters, a single cluster managed independently. 2. Federated clusters, multiple clusters managed under a single control plane, allowing resource sharing and consistency across clusters. 3. Managed Kubernetes services. Cloud providers offer fully managed Kubernetes services, such as Google Kubernetes Engine, GKE, Amazon Elastic Kubernetes Service, and Azure Kubernetes Service, AKS. Kubernetes use cases. 1. Microservices architecture. Efficiently manage, scale, and update microservices applications. 2. Continuous integration, continuous deployment, CI/CD. Automate application deployments and updates with tools like Jenkins, GitLab CI, and Argo CD. 3. Big data and machine learning. Manage distributed data processing frameworks, e.g. Apache Spark, and machine learning workflows, e.g. Kubeflow. 4. Edge computing. Deploy and manage applications at the network edge, closer to data sources. Kubernetes community and governance. Community. Kubernetes has a vibrant and active community with thousands of contributors from diverse backgrounds. Regular community meetings, special interest groups, SIGs, and working groups collaborate on various aspects of the project. Governance. The CNCF oversees the Kubernetes project, ensuring transparent and open governance. The Kubernetes Steering Committee provides project leadership and decision-making. Challenges and considerations. Complexity. Kubernetes can be complex to set up and manage, requiring a learning curve and expertise. Security. Ensuring cluster security involves managing access controls, network policies, and regular updates. Cost. Running Kubernetes clusters, especially in cloud environments, can be costly, necessitating careful resource management and optimization. Interoperability. Integrating Kubernetes with existing systems and workflows may pose challenges. Future of Kubernetes. Edge and IoT. Expanding Kubernetes capabilities to support edge computing and IoT use cases. Serverless architectures. Enhancing support for serverless computing paradigms, allowing developers to focus on code without managing infrastructure. Enhanced security. Ongoing efforts to improve security features and compliance with industry standards. AI and ML integration. Further integration with AI and ML workflows to streamline model training, deployment, and scaling. Conclusion. Kubernetes has revolutionized the way organizations deploy, scale, and manage applications. Its extensive ecosystem, strong community support, and continuous evolution ensure that it remains a critical technology for modern cloud-native applications.